Now it's recording.
Okay.
And we can start.
Okay, great. Thank you.
No
So,
problem.
hello to everyone again. Let me start this lecture. And I'll continue with digression on singularities of algebraic varieties. Maybe just one moment. I remember that I should better stop the video to make the internet signal better. Okay, so let me introduce a type of singularities which are reasonably good for us. Recall the following definition. An irreducible algebraic variety say X is said to be normal if the following two conditions hold. The first one is that X is almost smooth, which means that the singular locus is small. It has codimension at least 2. And the second condition says that small singularities of a function on an open subset are removable. Or more precisely, for any open subset U in X, and for any rational function f on X, if f is regular on U outside of a subvariety of codimension at least 2, then f is regular on the whole of U. Excuse me. So the small singularity along Z at Z can be removed. Actually, f extends to a regular function even in the points of Z. Okay, so this is the definition of a class of normal algebraic varieties. This definition is maybe not the one which you see for the first time in textbooks of algebraic geometry on algebraic geometry, but it is equivalent to the more standard one, which I'll come to, which I'll come at in a few minutes. This definition is more of geometric nature. The standard definition is more algebraic. So, in particular, all smooth algebraic varieties are normal. So, smoothness implies normality. And also you see that normality, from the definition, you see that normality is a local property. And therefore, it can be checked on affine charts. For affine algebraic variety, we have the following fact. An irreducible affine algebraic variety. Yes?
Why does smooth variety satisfy condition 2?
Well, actually, it is a theorem. I don't prove it. As about all standard facts from algebraic geometry, I refer to textbooks. This basically follows from the fact that regular local rings are integrally closed in the field of fractions. This is a theorem. This is not an obvious statement, but I won't prove it. Okay, so let me continue with the affine case. An irreducible affine algebraic variety X, let me stress that it is affine. It is important here. Is normal. If and only if the algebra of regular functions on X is integrally closed in its field of fractions, which is the field of rational functions on X. Integrally closed means the following. For any rational function f, satisfying a polynomial equation with a leading coefficient equal to 1, and the other coefficients being regular functions on X in the coordinate algebra of X. A polynomial equation like this with these GIs belonging to the coordinate algebra of X. If a rational function of S, or if a rational function on X satisfies this kind of equation, then it has to be regular. This is the condition that the coordinate algebra K of X in square brackets is integrally closed. Okay, so this is maybe the most standard definition of normality, which you probably have seen in textbooks. But the one which I gave is more geometric and actually more useful in applications. So I prefer this one, the one from above. Actually, there is a canonical way to turn an arbitrary irreducible algebraic variety into a normal one by a slight modification. Namely, there is the following statement. Maybe let me say that it is yet another fact from algebraic geometry, that if X is irreducible, if X is any irreducible algebraic variety, not necessarily normal, then there exists a unique, up to an isomorphism, normal algebraic varieties, say X tilde, together with a map, say nu from X tilde to X, called the normalization map. Maybe let me just call this procedure normalization. The construction of this X tilde is called normalization.
The map from X tilde to X
Yes.
has no requirement.
Yes, it has requirements, which I will formulate in a minute. Normalization. Construction. So this map has to be finite. A finite map. Finite means, for instance, proper map with finite fibers. So nu is finite and birational. Birational means that it is actually an isomorphism over an open subset of X. There exists an open subset U in X such that this map nu restricted on the inverse image of mu of U is just an isomorphism onto U. So such kind of maps which make open subsets of the two varieties isomorphic are called birational. So there exists a unique such normal X tilde equipped with a finite and birational map onto X, onto the given X, which is called the normalization map. So if X is affine, then the normalization of X is also affine. Since it is affine, it is determined by its coordinate algebra. And the coordinate algebra of X, the algebra of regular functions on X tilde, sorry, is just the integral closure of the coordinate algebra of X. So let me denote by tilde the integral closure of X, of the coordinate algebra of X in its field of fractions. So more precisely, maybe let me put it here on the next line. Yeah, okay. So more precisely, the integral closure of the coordinate algebra of X consists of those rational functions on X which satisfy a polynomial equation like the above one. Such kind of polynomial equations are called equations of integral dependence. So let me maybe put some sign here. So the equation of this kind I will mark by a star. Maybe in another color. Okay. So the set of all rational functions satisfying this kind of equation, these functions are called integral over the coordinate algebra of X, and the set of all these functions is the integral closure of this coordinate algebra in its field of fractions. So it is again a finitely generated algebra, and the respective affine variety is just the normalization of X. This is the affine case, and in general, normalization can be constructed by gluing normalizations of affine charts of X. So X is covered by finitely many open affine charts, and if you normalize each of them, then you can glue this normalization together along the common pieces, which are normalizations of the intersections of these affine charts. And you get the normalization of the whole X. Okay? So we shall usually impose the normality assumption on algebraic varieties under consideration. And in particular, when we speak about spherical varieties, so we shall assume that spherical varieties which we consider are normal. So for us, a spherical variety will always mean a normal spherical variety, unless otherwise is explicitly stated. And also, let me set a convention, which I should probably do at the very beginning of my course and seem to have forgotten to do, that all algebraic varieties under consideration are assumed to be separated. So the separation property for algebraic varieties says that if you consider the doubled variety x cross x, the product of x with itself, and you consider the diagonal in this product, so x can be diagonally embedded in x cross x. The separation property claims that this diagonal is closed in the product. This not always holds. There exist algebraic varieties which are not separated, but actually this separation property is important because it has many natural consequences, and we assume by default that all algebraic varieties are under consideration are separated. So for us, an algebraic variety,
Hey, Professor.
Yes.
Well, the separation means the diagonal of x times x is closed, or the diagonal map is a closed map.
Well, this is basically the same thing. Yeah, you may say like this: the diagonal map is the closed map. It is just the same. Closed map means the image of a closed set is closed, and in particular, the image of the whole X is closed. And this is sufficient to have the whole map, the whole inclusion map to be closed. So this is the same. Okay, so for us, an algebraic variety will always mean a separated algebraic variety. I should have put this requirement at the very beginning in order to avoid some nasty things, but let me do it now. Okay, so why normality assumption is important for us? It is first, it is rather mild because every variety, as we have seen, every variety can be canonically transformed to a normal one by a slight modification. And on the other side, normality has important consequences. Let me discuss one such crucial consequence, a crucial property of normal varieties equipped with an action of an algebraic group. So this is about line bundles. The property can be named as G linearization of line bundles. So suppose we are given a connected algebraic group, say G. Not necessarily reductive. Now the reductivity is not essential. Not necessarily reductive. Usually I denote by G a reductive, connected reductive algebraic group, but now it is not the case. Not necessarily Excuse my writing. And suppose we are given a normal algebraic variety X. So normality is essential here. Equipped with an action of G. So G acts on X. Then there is a following theorem. There exists an isogeny from G prime to G. So isogeny means a surjective homomorphism of algebraic groups with finite fibers, with finite kernel, you may say, you may formulate with finite fibers or finite kernel, this is the same. Okay, so there exists an isogeny from some other algebraic group G prime to G, such that for any line bundle, L over X, the action of G on X lifts to a finite to a fiberwise linear action. On the line bundle, on the total space of the line bundle, maybe not of G itself, but of its of this G prime. So briefly speaking, you may say that an algebraic group action on a normal variety lifts to any line bundle over it, maybe after replacing the acting group by its finite cover. So this lifting is called G prime linearization of this line bundle L. G prime linearization of L. So you may lift the action from the base to the total space of the line bundle. Okay. This is a general statement from algebraic groups, from the theory of algebraic groups, and I won't prove it because it takes some time and it is beyond the scope of this course. But I will give you a reference so you can find a good exposition of this proof, of the statement in an expository paper by Knopp. So here is the reference, a paper by Knopp. Kraft, Luna, and Wüst. with the title Local Properties of Algebraic Group Actions. Which was published in a series, in a German series, Deutsche Mathematiker Vereinigung, the abbreviation is DMV seminar, volume 13 of 1989. So this is a good reference for this theorem. And also let me indicate a corollary to this theorem. The corollary says that there exists a natural number n, m, such that under the assumptions of the theorem, such that the action of G on X lifts to the action of G itself, not of this G prime, but of G itself, but now not on the line bundle L, but on its mth tensor power. So if you replace each line bundle with its tensor power, one and the fixed for all line bundles, then actually you can leave the action of G itself from the base to the total space of each such line bundle.
Well,
yes?
How is the number m determined? It is not determined. It is independent of the line bundle, right?
Exactly, it is independent on the line bundle. Well, I can say what is this number, just if you understand the terminology. So far I didn't mention this, but I can say that this M is just the cardinality of the Picard group of G. The Picard group of G, if you know what is it, this will show up later in my lectures, but if you know for the moment what is it, the Picard group of G is always finite, and for M you can take its cardinality. For instance, if the coordinate algebra of G is a factorial ring, then this M can be taken to be equal to 1. Okay? So let me prove this theorem, this corollary. This is easy. If you believe in the theorem itself, then proving this corollary is easy. Proof. In the notation of the previous theorem, consider the kernel, denoted by Z, the kernel of the isogenic map from G prime to G. This kernel is a finite subgroup of G prime, and it acts trivially on X. Well, here I mean that if you have an action of G on X, then this action can be lifted to the action of G prime, of course, via this homomorphism. But the kernel of this homomorphism will act trivially. This is what is written here. And therefore, the action of Z on the total space of the line bundle L preserves the fibers. Each fiber is one-dimensional, and it follows that Z acts on each fiber, say the fiber over a point x small, via a character, say chi, which is just a homomorphism from Z to the multiplicative group of the field. So Z acts on these one-dimensional fibers by multiplication with this character. And now we can take for M just the cardinality of Z. And if we take this M, then we see that Z acts on fibers of the tensor power of the mth tensor power of L via the character chi to the power M. And this is identity, because it is a homomorphism from a finite group of order M, and if you take it to the mth power, it will be identical. Okay, and this, of course, implies that Z acts trivially on the total space of L to the M, and therefore the action of G prime.
Well, do we
L?
require the space X is connected?
I require X to be normal, and in my definition, normal assumes irreducible, in particular connected. Of course, you can define normality not only for irreducible varieties, but actually this reduces to each connected component. So by definition, I assume that normal varieties are irreducible. Okay? So let me finish the proof. Since the kernel of the isogeny acts trivially on the fibers, this means that the action of G prime on the tensor power of M, on the mth tensor power of L, this action factors through the action of the quotient group. Through the action of G. And this concludes the proof of the corollary. Okay. So any questions so far?
Professor, a silly question. What does
Yes, please.
preserves fibers exactly mean? I'm a little.
Excuse me, could you repeat, please? What do you ask about the fibers?
Preserves fibers. It means
Preserves fibers. Preserves fibers means that each fiber is mapped to itself.
No, it's Does
Yeah.
it need some condition to have this code? I'm just.
Let me start. Let me go through the lines of the proof again. So this G is the kernel of the map from G prime to G, and you have an action of G on X. So you can consider this action as the action of G prime, but G prime acts through this map. So G prime maps to G, and then G acts on X. This gives you an action of G prime, but this action of G prime is such that the kernel of this homomorphism, the Z acts trivially. Is it okay?
Yes.
And now the theorem, which was on the previous page, on the previous board, this theorem said that the action of G on X leads to the action of G prime on the line bundle, on the total space of the line bundle. But this action is compatible with the projection. So if Z acts on the total space of the line bundle, then each fiber over each point is mapped to itself, because the action on the point is trivial. The point X is mapped to itself by the action of Z, because of this trivial action. And this means that each fiber is mapped by Z to itself. Okay?
It's here because the theorem before that we can leave it to the G prime acts on.
Exactly. Yes. Yes.
Okay.
Yes. This is because of this theorem. I preserve the notation of the theorem. So this is the corollary of this theorem, and I preserve this notation. So we leave the action of G on X to the action of this G prime on the total space of the line bundle. Okay? Did I answer?
The character on each fiber are the same.
Say it again, please.
So the character of the Z action on each fiber, they are the same.
Well, yes, this is just by continuity. These characters do not depend on X. This is by continuity. But actually, this is even not important, because even if the characters were different for the fibers, even in this case, this property would hold, because this character is just a homomorphism from a finite group of order M to something. And if you take this homomorphism to the power M, then it will be identical.
So it is unitary. Okay, I understand.
But you are right that this character does not depend on the point X. You are right, by continuity.
Okay, thanks.
Okay.
By the connectedness of X.
Yes, of course, by connectedness of X. By connectedness of X. Yes. X is normal, hence irreducible by my convention, and therefore connected. Yes, sure. Maybe let me give you an example. Illustrating the theorem and the corollary. And in particular, this example will show that replacing G with a finite cover is really necessary. So let us take for G the group PGLN plus 1. This is the same as PSLN plus 1. And it acts on X, which is just the projective space of dimension n in the natural way. And we have a tautological line bundle L over X, which is classically denoted as O of -1. So let me recall that the fiber of this line bundle over a point, say P, in the projective space, this point is determined by a vector V, by a non-zero vector V in the vector space of dimension n plus 1. Non-zero, of course. And the fiber of the tautological line bundle over this point is by definition just the line spanned by this vector. So you see that there is no action of PSLN plus 1. There is no action of PSLN plus 1 on the total space of this line bundle L, but there is an action of SLN plus 1 on L. Let me write it like this. We have an isogeny from SLN plus 1 onto PSLN plus 1, an isogeny. And the group SLN plus 1 acts in a natural way on the total space of L. And this isogeny has the kernel, which is the cyclic group of order n+1, the group consisting of scalar matrices with determinant 1. This is a cyclic group of order n+1. And now if you take this line bundle,
SL n+1 acting on L.
well, it acts in a natural way because n+1, SLn+1 acts on this vector space Kn+1 of dimension n+1. SLn+1 acts here, and the fibers of this line bundle are just one-dimensional subspaces in this vector space. And the action of SLn+1 just permutes these one-dimensional subspaces. Okay? It is a natural action. So if you take the tautological line bundle to its n+1st tensor power, then you obtain the action of PSLn+1. So PSLn+1, excuse me. So sorry. PSLn+1 actually acts on the L+1st tensor power of L. Which is classically denoted as O of -n-1. So this illustrates the corollary of the theorem, that you can take a line bundle to some tensor power, one and the same, and you get an action of the initial group. And similarly, let me continue this example on the next page. Similarly, if you take any line bundle, an arbitrary line bundle over the n-dimensional projective space, it can be written, so all line bundles over the projective space are known, it can be written as O of k, which is by definition the -k tensor power of the tautological line bundle, O-1 tensor power minus k. So k here can be an arbitrary integer number. And on this line bundle L, there is an action of SLn+1, because SLn+1 acts on the tautological line bundle, and therefore it acts on its tensor powers. And if you take L, to the power n+1, as before, if you take any line bundle over Pn to the tensor power n+1, then you get the same as O minus n minus 1 to the power minus k. And here we have an action of the group. Here we have an action of the group PSLN itself. Because as we explained, PSLN acts on O minus n minus 1, and therefore it acts on each tensor power of it. So this shows us that this exponent to which we have to exponentiate to take the power of any line bundle, this is one and the same. It is independent of L. So if you take any line bundle over Pn to this tensor power, then you get the action of the initial. Okay, so this was an example. And Now let me come to an important application of this G linearization property. The following theorem is very important actually in in the whole theory of algebraic transformation groups, and in particular in the theory of spherical varieties. This theorem belongs to Sumihiro's theorem. This theorem says that let me keep the notation. Let me keep the previous notation. So my notation is that G is a connected algebraic group, not necessarily reductive, and X is a normal algebraic variety equipped with the action of G. So under these assumptions, the Sumihiro theorem says that any point of X possesses a G-stable quasi-projective open neighborhood. There exists a G-stable quasi-projective open neighborhood. Say U of the point X in the variety big X. So in other words, a normal algebraic variety equipped with an action of a connected algebraic group can be covered by G-stable quasi-projective open subsets. So locally, any such action is reduces to the quasi-projective case. So this is the statement of the Sumihiro theorem.
So even if the variety X is not projective, we have found a quasi-projective.
Yes. The point is that the variety X itself needs not to be projective or quasi-projective. Otherwise, there is nothing to prove, of course. The point is that X may be arbitrary, but normal. This is important. Normality is important. But under the normality assumption, so this statement is true. Other questions? Well, let me begin with the proof of the theorem. So the first observation, it is a trivial observation, is that, of course, there exists for any such point X small, there exists an affine open neighborhood of X small in X. A fine open neighborhood, say U prime of this point, of this given point X small in X. This is trivial. But of course, this U prime needs not to be G stable, just some open affine subset. Let me formulate the following lemma. This will be the first lemma in the proof. Lemma 1. The complement of this open affine subset U prime in X, let me denote this complement by D. D is the complement of U prime in X. It is a closed subvariety, and if we decompose it into irreducible components, D1, etc., ds. So these di's are just irreducible components of D. Then each of these di's has codimension 1 in X. So the complement of an affine open subset in X is a union of irreducible subvarieties of codimension 1. such kind of an algebraic variety is called a hypersurface or divisor. Maybe you know some of these names. You should know. You should hear at least these names if you are familiar with basic algebraic geometry. And our aim is to prove, maybe you even know this lemma, but let me prove it just for the sake of self-consistency of my lectures. Let me prove this lemma for you, but let me do it after the break. So now it is the time for a 10-minute break, and let me prove the lemma after this break. Okay, so let me stop the first half of my lecture, and if you have any questions, then please go ahead. Any questions or comments?
We call an isogeny a finite cover.
Yes, so this is another name. Yes, isogeny is a name common in the theory of algebraic groups, but of course you can call it a finite cover. The point is that this map is an algebraic group homomorphism. It is just not only a map of algebraic varieties, it is a group homomorphism. And by the way, here I should say that G prime should be also connected. G is connected by assumption, and this covering group should be also connected. Okay, let me write it here. Other questions?
Professor, I want to ask about the example below.
Yes.
Yeah. On the first question is, I'm confused about the name of how to say tautology.
Tautological. Let me write it. Let me write it for you. Tautological. Tautological.
Can I ask why it is called this name? And I'm a little confused when
I mean, because it is the very first line bundle you can imagine on a projective space. So if you are given a projective space and you ask yourself, how can you construct a line bundle on it? Then the most obvious way is to take this one. Because each point of a projective space is just a line in some vector space, and you take this line as the fiber of the line bundle over Pn. This is how I would explain this name. I don't know if this convinces you, but this is my explanation. I don't know any other explanation. Okay. More questions? Remarks?
So the reason that we don't have the projective SL n plus 1 action on L is because
well, because I would say that how to say. So you may ask a more general question. If you have this kind of picture, so if the action of G on X lifts to the action of G prime, then you may ask how unique is this lifting unique? To which extent this lifting is unique? And what you can see more or less immediately from the definition that the lifting of the action of G to the action of G prime on L is not absolutely unique. It is unique up to multiplication with a character of G prime. Okay. Because what you can do, if you have some lifting, so suppose your G prime acts on L. If you have such a lifting, then you can multiply the actions with any character of G prime. This character just acts by dilations, by scalar multiplication on each fiber. And therefore, this action descends trivially to X. So you get the same action of G on X, which you started from. So concluding, we see that any two actions of G prime on L, which lift the action of G on X, any two such actions differ by a character. And now, if you come to this example, then you see that you have an action of SLN plus 1 on L. This is the obvious one. But this action does not descend to the action of PSLN plus 1. And any other action of SLN plus 1 on L, on the total space of the tautological line bundle, which you can imagine, this action should differ from this one by a character. But SLN plus 1 has no characters. So in this case, the lifting is unique. There is some kind of noise. I hope you hear what I have just said. So the point here is, let me briefly repeat that the point here is that the lifting, the lifting of the PSLN plus 1 action on the projective space to the SLN plus 1 action on the tautological line bundle is unique because SLN plus 1 has no characters. In particular, this means that you cannot lift the action in a different way so that this group would act on SLN plus 1. On the tautological line bundle. This is my explanation. So was it clear?
SLN plus 1 has no character.
Yes, SLN plus 1 has no characters because it coincides with its commutator subgroup. SLN plus 1 coincides with the derived subgroup.
A simple group, right?
Yes, it is a simple group. Well, simple algebraic group. It is not simple in the sense of abstract group theory because it has finite normal subgroups, but it is simple as an algebraic group. It is a simple algebraic group, and therefore it has no characters. Okay?
SLN is simple. And so what about PSLN? Also simple.
PSLN is also simple, and PSLN is even simple as an abstract group. It has no non-trivial normal subgroups.
I know PSLN is simple as an abstract group. So in algebraic group theory, we can have a group and its quotient both simple as an algebraic group, right?
Yes, sure. The point here is that you take a quotient by a finite subgroup. So finite subgroups are ignored in a sense in this situation. So when you discuss simple algebraic groups, you ignore finite normal subgroups.
Oh, final question. The separation axiom says that the diagonal is closed in x times x, right?
Yes.
Well, this is almost the same as the Hausdorff property of a topological space.
Exactly. Yeah.
But I heard from somewhere that the reason we don't call separation Hausdorff because separation is not the same as Hausdorff. But if you define that the separation, the variety x is separated if its diagonal is closed, then it is the same as the Hausdorff space. So what is Hausdorff different from separation?
Yeah. Let me explain what is the point here. So if your base field is a field of complex numbers, then on any algebraic variety X, you have two kinds of topologies. You have the Zariski topology, and also you have
the normal analytic topology right now.
Yes, and you have the analytic topology. So the analytic topology on X is Hausdorff. It satisfies the Hausdorff axiom. But the Zariski topology is never Hausdorff because Zariski open subsets are big. So when you consider X cross X, you can equip it with the analytic topology, which is just the product topology of two Hausdorff spaces. But also you can.
In this case, the X times X is equipped with Zariski topology, not the product of the Zariski
Exactly.
topology.
The Zariski topology on X cross X is not the product topology. Yeah. So the property that the diagonal is closed refers to the Zariski topology. And since the Zariski topology is not the product topology, this property is not equivalent to saying that X is Hausdorff. If the topology on X cross X were the product topology, then this closedness condition is exactly the Hausdorff condition. But since the Zariski topology on the product is not the product topology, this condition is different. This is this is the point. Okay. Well, I think that the break is over and it's time to continue the lecture, the second half of the lecture. So let me go to the proof of this first lemma. I will argue by contradiction. So suppose there exists an irreducible component of this D, so some di, which has codimension at least 2. Let me draw a picture for you. So here is my X. I have this D consisting of several components. So
Professor,
some of this, yes.
So we want to prove that there is a finite open neighborhood of X, and its complement is codimension 1, or I mean,
its complement. So the lemma states that the complement is of pure codimension 1, which means that all its irreducible components are of codimension 1.
No,
I want to prove this.
Whether we choose open affine neighborhood first.
No. It holds for any affine neighborhood, for any affine open subset. But we apply this lemma to an affine open neighborhood, which we have chosen from the beginning of the proof. So this is a picture for irreducible components of this D. So some of them may have codimension 1, and suppose that one of these components, say some di, has a smaller dimension, has codimension at least 2. Excuse me, let me draw it better. So one of these di's has codimension at least 2. This is my small component. Choose now an affine open subset, yet another affine open subset, U double prime in X, which intersects this small component di which intersects this di, and which doesn't intersect all other irreducible components of D. So this intersection is non-empty, and all other intersections are empty.
How can we choose that?
Well, just because you may remove all other components from X, so you may remove all other di's from X, and you obtain an open subset of X. It is not necessarily affine, but inside this open subset, you may choose an affine neighborhood of any point of this di, because affine open subsets form a base of the Zariski topology. Every open subset is the union of affine open subsets. So you can choose a small affine open subset, so this U double prime, which doesn't intersect all other irreducible components. So these di's are removed from the picture. Okay? Well, so having chosen this, consider the intersection. Maybe I have some place to write it here. The intersection of U prime and U double prime. So U prime is the complement of all D, components, of the union of all components of D. And U double prime is an open subset which intersects only one of these components. So the intersection, let it be U triple prime, U three primes. It can be written in two ways. It can be written as U double prime minus di, and also it is the same as U prime intersect with U double prime. It is, as an algebraic variety, it is isomorphic to the intersection of the product U prime with U prime and U double prime with the diagonal of X. The product of two affine varieties is still affine, so this guy is affine. And the diagonal is closed in the cross product X by X by the separation property. So we get a closed subvariety in an affine variety, and it is again affine. The intersection of two affine open subsets in a separated algebraic variety is again affine. Okay? Now, so let us memorize this picture. So what do we have? We have an affine algebraic variety. Let me elaborate a little bit on this. We have an affine algebraic variety U double prime. We remove something small, which has codimension at least 2, and we get again an affine open subvariety U triple prime. Let us memorize this picture, and then to continue, this inclusion of U triple prime into U double prime gives rise to the inverse inclusion of coordinate algebras. So the coordinate algebra of U triple prime is contains maybe is equal, but contains the coordinate algebra of U. Maybe let me write it with more details. So the inclusion of U triple prime into U double prime this inclusion is strict because you throw away some smaller subvariety which is non-empty, this di. This inclusion of u triple prime into u double prime gives rise to the inverse inclusion of coordinate algebras. Okay, but now if you take any function f which is regular on this smaller open subset u triple prime, it is regular. This means it is regular outside the intersection of di with u double prime. And the codimension of this subset is at least 2. Since you have a function which is regular outside as a subvariety of codimension at least 2, the normality assumption implies that actually f is regular on the whole of u double prime. This means that actually, hence, the coordinate algebras of these two affine varieties coincide. And since a map, an inclusion map of affine algebraic varieties gives rise to the identity map on the coordinate algebras, this means that this map is also identical. In other words, u triple prime must coincide with u double prime. But this is a contradiction. Because u triple prime is obtained from u double prime by removing this intersection. So it is a smaller open subset, but we have proven that it has to coincide with u double prime because the regular functions on these two affine open subsets are the same. So this proves the lemma. Any questions on the proof, maybe? So no questions so far. Okay. Now, let me again come back to the formulation of this lemma. So what we have done, we have chosen an affine open neighborhood of this given point in my variety x, and we have proved that the complement of this affine open neighborhood is a hypersurface. It is a union of irreducible subvarieties of codimension 1, a hypersurface or a divisor in other language. And now I want to associate a line bundle with a divisor d, a line bundle of x over x associated with this divisor d. To this end, let me remind you of the relation between divisors and line bundles. Again, I hope that you basically know what I'm going to remind, or at least you heard about it. But anyway, let me make this digression for the sake of completeness. So now comes a digression on divisors and line bundles on algebraic varieties. So let X be any normal variety. A prime divisor on X is by definition an irreducible closed subvariety of codimension 1. Say D in X of codimension 1. A wild divisor on X is by definition a formal linear combination of prime divisors with integer coefficients. A formal Z-linear combination of finitely many prime divisors. Say delta equals to K1 dot D1 plus etc. plus Ks dot ds, where Ki's are integers and Di's are prime divisors. Actually, we shall usually drop this adjective while divisors are often called just divisors. So we just say that this guy is a divisor on X. So this is a formal linear combination. So there is no algebraic, so far there is no algebraic or geometric sense in multiplying the divisor, the prime divisor, by an integer. So far it is just formal. Well, so a bit some more piece of terminology. A divisor is called effective. What is an effective divisor? We shall say that a divisor delta is effective, and we shall write that delta is greater or equal than 0. In other words, you can call it non-negative. If all coefficients, if in this linear combination, are non-negative. Okay. Well, let's go on. So a prime divisor delta, a prime divisor D, any prime divisor D, is as an irreducible subvariety of codimension 1. This means that it has to intersect the regular locus, the smooth locus of X. The intersection of D with the smooth locus of X is non-empty, because the singular locus of X has codimension at least 2. Since X is normal. And there is the following property. So for any point for any point x small.
Well, we require that the divisor does not intersect the singular part, right?
No, it may intersect. It may intersect the singular locus. Of course, usually it does. It is not a requirement. It is a statement that any prime divisor intersects the smooth locus, because the smooth locus is a big open subset. Its complement is of codimension at least 2. If a divisor D would not intersect the smooth locus, it would be contained in the singular locus, but this is impossible because the singular locus has codimension at least 2, and the divisor D has codimension 1. So any prime divisor has to intersect. This is a claim, a property that, let me maybe write it explicitly. So it is an obvious claim that any prime divisor should intersect the regular locus of x. And yet another claim is that for any point in this intersection, for any point on a prime divisor, which is a smooth point of x, there exists an affine open neighborhood of this point say U, such that if you consider the coordinate algebra of this affine open subvariety and consider the vanishing ideal of D in this coordinate algebra, this ideal, this vanishing ideal of D, it consists of all functions over U which are 0 on D. The property is that there exists such an open affine neighborhood U, such that this ideal is principal. It is generated by a single function, say T sub D. In other words, so let me maybe draw a picture for you. So you have your x, you have a divisor D, prime divisor D in x. You have a point here which lies in the smooth locus of x. Maybe I will not draw the smooth locus. Instead, I will draw this affine open neighborhood U. So the property which I stated says that the intersection of D with U, it is a prime divisor in U, is given by a single equation in the strong sense. Not only D consists of those points, D intersect with U consists of those points on which this function T sub D is equal to 0. Even more, this function generates the ideal of all functions on U which vanish on D. So this T sub D can be called a local equation for D in this strong sense. And now, for any rational function on X, there exists an integer k such that this function can be represented as T sub D to the power k times a function g which is defined in a neighborhood of x. So it sits in the local ring of this point x small. And it is non-zero at this point. Basically, what can you do? If this function f is defined on U, then you may divide it by this equation of D on U as many times as it is possible. You mod out this factor t sub d to some power k, and what you get what you get left is a function which is not in this ideal. You cannot divide.
Well, Professor, the factorization of x into the case power of td and g is local, right?
Yes, everything is local. Yes, everything is local. So this factorization is in some neighborhood of this point. Everything is local. I just wanted to explain how this factorization comes from this property, that this ideal is principal. Let me repeat that if you take f regular on U, then you can divide this f by t sub d as many times as it is possible. And what you get left a function g on U, which does not vanish on D. And this means, in particular, that yeah, maybe I skip some details here, but this statement is true. This is what you can do on U, and if your function is not defined on U, then you can represent it as a quotient of two, as a ratio of two functions defined on U. And you divide these two factorizations one by another, and you get this kind of factorization with integer power. Anyway, this property holds true. And this number k, denoted like this, is called the vanishing order of the function f along the prime divisor D. So if k is positive, then we say that f has 0 along D. If k is negative, we say that f has a pole along D. Okay? Now we can associate to each rational function on X a divisor, which is called the principal divisor. So what is a principal divisor? Precisely the divisor, let me denote it like this, the divisor of a rational function on X. It is the formal linear combination of prime divisors with coefficients equal to vanishing orders of the function f along these prime divisors. there are actually only finitely many divisors for which this vanishing order is non-zero. So this is a finite sum. And this kind of divisor is called the principal divisor associated with the function f. It can be decomposed as the difference of two effective divisors, the divisor of zeros and the divisor of poles. So let me call this guy, excuse me. Let me call this guy the divisor of zeros. It consists of those summands for which these vanishing orders are positive. And this guy is the divisor of poles. And this guy is consists of those summands in this formal sum, for which the vanishing orders are negative, but we take these coefficients with the opposite sign, so we subtract here, so that both these divisors are effective. Both are effective. Okay, this is what is called a principal divisor, and the normality assumption implies that a function f is regular on the whole of x if and only if it has no poles. In other words, the divisor of poles is zero. Okay?
So why do we need normality to derive this?
Well, I mean, otherwise it is not true. So if your variety is not normal, you can there exists a function which is defined everywhere outside a subset of big codimension. So its indeterminacy locus has codimension bigger than 1. And this means that it has no poles. There are no prime divisors with vanishing order negative along this divisor. But still, this function is not everywhere determined. It is not regular on the whole X.
The singular focus of a function on a non-normal variety can have codimension greater than 1. Oh, I see.
No, even the singular locus may have but it is not actually the question of codimension of the singular locus. Even if the singular locus has codimension greater than 1, it may happen that your variety is not normal. So normality here is essential because of this this second condition, because normality is used here.
I mean, if f is defined outside a set of codimension no less than 2, then f can be extended to that set.
Exactly. This is the point. Yeah. So now let me define what is a Cartier divisor. Let me remind you what is a Cartier divisor.
Professor,
yes,
we do not prove that. Do not prove that the principal ideal condition, right?
Yeah. Actually, here I do not prove almost everything because this is a standard material from algebraic geometry, and I refer to textbooks for the proof.
Okay.
I just remind you basic facts almost with no proofs. Okay. This is no more than just a reminder for you. Okay, so let me remind you now what is a Cartier divisor. So before we worked with Weil divisors, and what are Cartier divisors? A Cartier divisor, briefly speaking, a Cartier divisor is a Weil divisor which is locally principal. Or more precisely, it is a divisor delta such that for any point in X, there exists an open neighborhood of this point, say U, such that the intersection of your divisor with this neighborhood is principal. So Cartier divisor is a divisor which is not globally principal. There may not exist a function f on the whole of X such that the divisor is of this form. But locally, this property holds. So in a neighborhood of each point, this divisor can be represented in this form. This is what is called a Cartier divisor. And actually, if your variety X is smooth, let me remark that if your variety X is smooth, then any Weil divisor is Cartier. Because of this property that any prime divisor is Cartier, because it is defined by a single equation in a neighborhood of each point on a smooth variety, yeah. And any other divisor is a linear combination of prime divisor, and a sum of Cartier divisors is still Cartier. You can just multiply the equations for the divisors taken to the respective powers, and you get a function giving you that your divisor is principal. Okay, so for smooth varieties there is no difference between Weil and Cartier divisors, but for singular normal varieties there is a difference. So we have to take care about this distinction.
So in the smooth case, you can always find the local equation of a divisor.
Exactly.
Even if it is singular itself. So the divisor
No,
is
it doesn't matter whether the divisor itself is singular or not. It matters whether the point X is smooth or singular on big X. So this does matter. That you take a point from the smooth locus of X. This is important. Okay. So now let me discuss the relation between divisors and line bundles. So suppose you have a line bundle. So suppose you have a line bundle on your X, line bundle L on your variety X. And suppose you have a section of this line bundle, which is not everywhere defined. It is not a global section. It is a rational section. It is defined on some open subset of X. Then, since every line bundle is by definition locally trivial, you can find an open cover of X by some open subsets UI, open cover, such that the restriction of your line bundle over each of these open subsets is trivial. The total space of the restricted bundle is just the product UI cross the one-dimensional vector space. And therefore, the section S restricted to this subset UI gives rise to a rational function f sub I on this open subset. It is a rational function, not a regular function, because the section S is defined only on U, on this U. And its restriction on UI is defined on the intersection of U with UI. So this section S restricted to UI is not everywhere defined on UI. This means that this trivialization associates not a regular function, but a rational function with this section.
The right part of the trivialization is UI times K1, right?
Yes, of course. This is a fiber. K1 is the fiber. All fibers are the same. They are identified with one and the same vector space. This is the trivialization. And this rational function fi takes a point in UI to some vector in this fiber, so to some scalar. This is the rational function. And of course, the rational functions on UI are the same as the rational functions of the whole X. This doesn't matter. If you have two different trivializations over UI and UJ, then on the intersection of these two domains, UI and UJ, these functions may differ. But they differ by an invertible function. So the ratio of AY over FJ for two different indices, Y and J, is a function which is defined on the intersection UI with UJ, and it is invertible. So you may define the order, the vanishing order along a prime divisor D of this section S by definition taking the order, the vanishing order of this function fi along D. If
the sum of the order of fi or the single
no, D is a prime divisor. In my notation, D is a prime divisor, so there is a single order. You need not to take the sum. If D intersects with UI, if D intersects with
the order of different fi with respect to D is the same, right? Oh,
yes.
Invertible function, yes, I see.
An obvious remark is that this number does not depend on I. Because if you take another index, fj, say, if you take fj, then fj differs from fi by this invertible multiple. This function is invertible, and its divisor is 0. It has neither zeros nor poles on this intersection. So the order of a section is well defined. The order of a section along a prime divisor is well defined. And now you can define the divisor of the section D, of the section S, in the same way as the divisor of a function. It is just the sum over all prime divisors D, the sum of these divisors taken with coefficients equal to the vanishing orders of the section along these divisors. And this divisor is Cartier by construction. Because locally, the section S is represented by this function. On each of these neighborhoods, on each of these UIs, this section S is represented by the function fi. and therefore on the open subset UI, this divisor is principal. So globally, this divisor is Cartier. An easy observation is that if S is a global section, that is, it is the section of your line bundle over the whole of X, then the divisor of S is effective, and vice versa. The section S is global, everywhere defined, if and only if it has no poles, because it is true locally. So, so the section is global if and only if it is defined everywhere on each UI. And on the UI, this section is identified with this function, and for functions we know this property. So this is a criterion for a section to be global.
I missed something. Well, how do we prove that the divisor with respect to S is Cartier?
Because locally, on each of these,
I see.
On each of these open subsets, this section is identified with a function.
Yes, I see.
Okay, good. Let's go on. I have not much time left, so let me a bit hurry on. Conversely, given a Cartier divisor delta, there exists a pair of line bundle over X and a rational section S of this line bundle, such that the divisor of this section S is equal to delta. So any Cartier divisor is of this form. Any Cartier divisor corresponds to some section, corresponds to some section of some line bundle. Any Cartier divisor is of this form. Okay? And actually this pair is unique up to an isomorphism. So to each Cartier divisor, you can canonically associate a line bundle and a rational section of it, such that the divisor of this section is your Cartier divisor, your given Cartier divisor. So this line bundle is denoted usually like this, or just simply like this. And the section is denoted like this, as subdelta. Now, let us consider the space of global sections of this line bundle over X, and consider a finite dimensional subspace in it. Okay? The choice of a finite dimensional subspace in the space of global sections of your line bundle L gives rise to a rational map say phi from X to the projective space, which is the projectivization of the dual space M star. The points in this projective space are the same as hyperplanes in M, because a point in M star is determined by a vector in M star, by a non-zero vector in M star, that is by a linear function on M up to a multiple. And this linear function on M up to a multiple is determined by its kernel. The kernel is a hyperplane in M. So the points in this dual projective space are just hyperplanes in M. And this map phi takes a point X to the hyperplane, which I denote M of X, which is just the space, the subspace of all sections in M, vanishing at the point X. For some points, all sections from M may vanish at this point. And therefore, this M of X will be the whole M. And these are the points in which this map is not defined. But for the other points in an open subset of X, some sections from M do not vanish at this point. And the vanishing subspace is just a hyperplane. So this guy is a hyperplane in M, that is the point in the dual projective space, or M itself, or the whole M, in the points where this map phi is not well defined. This is the indeterminacy locus of this rational map. You may view this map more concretely in projective coordinates. In projective coordinates, so let us choose a basis, say S naught, etc., Sn, a basis of this finite dimensional subspace of global sections of this space M, then this map phi is given by taking a point X to a point in the projective space with coordinates S naught of X, etc., Sn of X. These S naught, Sn are sections of your line bundle, and their values at a point are vectors in the fiber of this line bundle over the point X. So this value sits in the fiber L sub X, and all other values also do. But this fiber is a one-dimensional vector space. It is isomorphic just to the base field, well, to the power 1. It is a one-dimensional vector space. Of course, this isomorphism is not canonical. You may change this isomorphism by a scalar multiple. But since you are considering a point in the projective space, when you multiply all coordinates by one and the same scalar multiple, you do not change the point. So this is a well-defined map. And this is the coordinate version of the map which I described before in a coordinate-free way. Well, I think that I have to stop now. I have a few things to be said more about this correspondence between divisors and line bundles, but let me postpone this for the next lecture. So let me stop now. Thank you. If you have any questions, yes, then please.
How do we construct the line bundle from the Cartier divisor?
Well, again, I can say that I can advise you to take a look in a textbook in algebraic geometry, but let me say a few words. Let me say a few words about this. Let me come back to this picture. Of course, here the setting was a different one. You have started from a line bundle, and then you constructed a Cartier divisor of a section. But anyway, I shall use this notation. So suppose you have a Cartier divisor. This means that you have. Let me show you here. This means that you have an open cover of X by some open subsets U sub I, such that the restriction of your divisor on each open subset Ui is principal. Yeah, so what is a Cartier divisor? Cartier divisor is a divisor such that its restriction on an open neighborhood of each point is principal, right? So you can cover your X by these open neighborhoods. So that the restriction of your delta on each of these UIs is principal. And if it is principal, it is given by a rational function, sum fi. If you have two such open neighborhoods, ui and uj, you have two rational functions which define one and the same divisor on the intersection of these neighborhoods. And since these two rational functions define one and the same divisor, their ratio is an invertible function.
So that's
Okay?
the transfer map, right?
Exactly. And these functions, fi over fj, will be the transition functions between different trivializations of your line bundle. So your line bundle is defined by trivializations over these ui's and by these transition functions. Okay? More questions? So again, let me repeat that if you have any questions after the lecture, you can, at any time, you can write me on email. Unfortunately, I didn't succeed to get subscribed to the WeChat. This was too complicated. But do not hesitate to write me on email. Some of you do, but if you have questions, then you can do it at any time. I will answer promptly all your questions. So, are there any more questions or comments on what we have seen today? There is something in the chat. I don't know if it. Yeah, by the way, if you want to ask me questions, then it is better to do it orally, because during the lecture, I cannot efficiently look in the chat. So if you want to ask something, if you want to ask me about something, then just say it. It's better not to write in the chat. I see some questions in the chat. So, for instance, the last one from Mike is, I guess, it is about the proof of the first lemma, whether u triple prime is bigger than u double prime. No, it is smaller than u double prime, because it is obtained from u double prime by subtracting something, by subtracting the divisor di. Not divisor, but this smaller dimensional subvariety di. But anyway, if you want to ask me, it's better to do it orally.
Professor, may I ask the relation of wild divisor and Cartier divisor? Yeah.
Yes.
So let me see. So Cartier divisor is not necessarily a wild divisor.
No, Cartier divisor is a particular case of a wild divisor, at least under my assumptions. I consider everything on normal varieties, normal algebraic varieties. Under these assumptions, Cartier divisors are a subset of wild divisors. This is, so you see the definition here. So a Cartier divisor is a wild divisor, which is locally principal.
So here we need the assumption of normal, right?
Well, you may say something without this assumption. For some things, it is enough to say that the singular locus is of big codimension. It is weaker than normality. But let me not get involved in this in these technical details. Let me, for simplicity, assume that X is normal.
Yeah, because before I'm heard that Cartier divisor is used in the more general situation, like in some not necessarily normal scheme.
Right. You can consider these things in more general situation, but I don't need this for my purposes. Yes, you are right.
Yes.
So, more questions or comments?
So in the more general situation, may I ask, like the Cartier divisor is still locally principal, right? So we may say like this, or we need another modification of the definition.
Well, I would say that if you want to consider Cartier divisors in the general case, then basically a Cartier divisor is defined by this kind of data, by an open cover and a set of rational functions corresponding to these open subsets, such that their ratios are invertible on the intersection of these open subsets. So in some other terminology, it is a cohomology, first cohomology class of the sheaf of invertible functions on X. And this is more closely related to line bundles over X. So this correspondence between Cartier divisors and line bundles goes over the normal, non-normal case, but you have to modify the definition of a Cartier divisor. Just by basically you define the Cartier divisor as the collection of such functions, well, up to some identification, up to change of this open cover. So it is nothing but the cohomology class, the Czech cohomology class of the sheaf of invertible functions on X.
So in the more general case, the Cartier divisor is associated to the invertible sheaf, and it's we can associate to the line bundle. Yes,
because invertible sheaves are more or less the same as line bundles. For any line bundle, its sheaf of sections is an invertible sheaf, and vice versa. Any invertible sheaf arises from some line bundle. These objects are equivalent.
Okay. Thank you.
Okay, thank you for your question. More questions? Well, if there are no more questions or comments, then maybe we can stop this lecture. And let me say that at the beginning of the next lecture, I will take a few minutes to discuss some more things about the relation between divisors and line bundles, and about this rational map defined by a finite dimensional subspace of sections of a given line bundle. I will say a bit more about this picture. And also I will finish the proof of Sumihiro's theorem. And after that, I'll turn to spherical varieties. And I hope to prove a finiteness theorem for spherical varieties, saying that given a spherical variety, the number of orbits, of G orbits on it is finite. There is also a converse statement, which is more complicated. I am going also to prove it, but I'm not sure that I will manage the second theorem on the next lecture. But anyway, this is my next goal. So, if there are no more questions, then let me stop sharing. And I hope to see you all on Wednesday. So, see you on Wednesday, and bye-bye.